Moving to the production function, this is going to be our primary way that we model how producers combine capital and labor to produce output. So our production function here is specifically a mathematical relationship. And as I've just said, it describes how output is made from different combinations of inputs. We're going to represent the production function generally by saying that output is a function of capital and labor, where Q is the quantity of output, K is the quantity of capital used, and L is the quantity of labor used. The production function can look many different ways. I've included two more simple examples here on the slide. So the first one we have is quantity or output equal to 10 times the amount of capital used plus 5 times the amount of labor used. In this production function here, capital and labor are substitutes. You can produce output with either just capital, just labor, or a combination of both. Right? If we were to take this production function and substitute 0 for each of our inputs, so let's start with labor. So we'll say quantity is equal to 10 times K plus 5 times labor, which we've said equals 0, right? We don't want to use any labor, just capital, right? We still are able to produce output, right? Similarly, if we substitute 0 for capital, right, that goes to 0, we can still produce output. The second example here is a version of the Cobb-Douglas production function that we'll turn to in just a second. And here, capital and labor are complements. You need both of them for the good to be produced. If we substitute 0 for one of our inputs, right, so let's do labor, right, we're going to have quantity of output is equal to capital to the 1/2 power times 0 to the 1/2 power, which is going to go to 0. Capital to the 1/2 power times 0 goes to 0, and we get no output. Similarly, if we substitute 0 for capital, we're going to not get any output, right? 0 to the 1/2 power is 0. 0 times L to the 1/2 power is 0. So again, we get no output. So when capital and labor are substitutes, you can use one or the other or a combination of both. When they are complements, you need at least one of each, right, for output to be made. And that's what our Cobb-Douglas production function shows. And for the most part, that's going to be true for any production function. You need some capital and some labor. Very rarely can you only use one input and still produce output. Looking at our Cobb-Douglas production function in more detail, I've included the general form of the Cobb-Douglas production function here. So it's quantity of output equal to capital to the alpha times L to the beta, right? This is the version of the production function that's most often used in economics. It has really nice mathematical properties that you'll see when we get to the cost minimization portion of the chapter. But it actually also describes real life production data really well. So it's very convenient to use in that it describes the world and is functionally useful. Most often, we're going to see that those exponents on capital and labor sum to 1. So something like you saw in the previous slide where each was equal to 1/2, right? 1/2 plus 1/2 is 1. You might also see Q equal to K to the 1/3 power times L to the 2/3, right? 1/3 plus 2/3 is 1, right? So those types of forms. And this is what you're going to see most often in this class, the Cobb-Douglas production function with exponents that sum to 1. An example I like to use for thinking about what type of production we'd model using this production function is mowing the lawn, right? So if we look at our guy over here, he's pushing a lawnmower. And in the activity of mowing the lawn, labor and capital are complements. If you take the guy away, right, and we only have the lawnmower, it's not going to move on its own. Or if it does, it's going to be erratic, right? It's not going to do a good job or complete job. If instead we leave the guy and take away his tool, take away the lawnmower, he on his own, again, can't mow the lawn, right? Maybe he can rip out the grass with his bare hands, but that's not what we're looking for here, okay? So when it comes to Cobb-Douglas, we have, again, capital and labor working as complements. You need both together for the output to be produced. Now we're going to turn to the short run production function. So remember, in the short run, we're assuming that capital can't change, that it's fixed. Labor is the only thing that changes. So to represent that, we add this bar over the K to indicate that it's constant, right? It cannot change. And so our production function now includes that bar over the K. So we have output is equal to K bar to the alpha times L to the beta. This lets us consider how production changes, how output changes as we vary the amount of labor used while keeping the amount of capital used the same. So this lets us get to what we call, again, the ceteris paribus assumption. This is an R. Let me rewrite that. Okay. Ceteris paribus means that we're only changing one thing at a time, and it's what's necessary for any type of causal analysis. If more than one factor changes, we can't say what the impact of any of the things that changed really was, right? It could be all one, it could be all the other, it could be a mix of both. So by holding everything constant and changing only one thing at a time in our models, lets us see what the impact of that change really is. Before we turn to production in the short run in the next video, I want to show you an important metric that we're not going to actually be using much, but it does hold an important place in the business world, and it's the average product of labor or the average product of capital. We're going to focus on labor here, but in general, average product is what business owners use to figure out how profitable their process is, right? Is it cost efficient or not? So to find average product here, again, we're focusing on average product of labor. We're going to divide total output by the number of workers hired, the amount of labor used. Okay, we could do the same for capital. It would be average product of capital equal to the amount of output over the amount of capital used. Okay, but for right now, we'll focus on average product of labor. So let's say that we have a Cobb-Douglas production function, and we'll say that it's quantity equal to K to the 1/2 power times L to the 1/2 power. Our average product of labor here, again, is quantity over labor. We're going to set that equal to capital to 1/2 power times L to 1/2 power all over L, right? And note here that this L has a 1 exponent. So if you remember your properties of exponents, if you have the same base, in this case, we have L in the numerator and the denominator, so the same base on both sides of our fraction, then we subtract the exponent on the base in the denominator from the exponent on the base in the numerator. So this gets us capital to the 1/2 power times labor to the 1/2 power minus 1. Okay, simplifying further, we get capital to 1/2 power times L to negative 1/2 power. All right, we can leave it like that if we want, or we can rewrite it. Okay, remember that this negative exponent means that our labor variable is actually in the denominator. So we can rewrite this as capital to the 1/2 power over L to the 1/2 power. And then if we want to simplify further, we can put capital over labor in parentheses and say that's all to the 1/2 power, okay? And that gets us the average product of labor. So we're going to stop there. Oh, excuse me, we have one more slide. A couple more slides, actually. All right, so we'll keep going. Oh, no, I was correct. So we're going to end here, and then in the next video, we'll pick up with marginal product.